find is this van der Waals equation. And when we decided to talk about there were these isotherms, and it looked like this and then went like this. And the issue was about this region over here. And when it was this region over here, that there is a question of coexisting liquid gas phases, and therefore there are large fluctuations in the system. So large fluctuations in some region of space.
Sir?
Yes.
So I think there is a sound problem with the mic. It's making some noise.
হ্যাঁ স্যার স্যার সাউন্ডটা ভালো করে আসছে না।
So the sound is fine. It's just
a certain region of space, there is a gas phase somewhere and there is a liquid phase somewhere. The van der Waals equation of state says that it is P plus A over V squared, V minus B is equal to RT for 1 mole, and certainly does not recognize this. So that's an interesting issue, that there is this description of the liquid gas critical point which the van der Waals equation is offering to you. But when you are in this region over here, then it is not a one-phase region, which means that there is fluctuation. And if you are going to talk about fluctuation, you see that the equation itself doesn't have any fluctuations. So it describes this critical point all right, but does not, without talking about the fluctuations which are inherent in this description, that we are talking about T minus Tc magnitude being of the order of millikelvin or less. And the point is that in this region over here, the coexisting phases means the density is not uniform, and uniform density means that pressure cannot be uniform either, but this equation does not have that feature. So and because it does not have that feature, the error that it makes is in calculating the critical exponents. It gives you beta equal to 1/3 and gamma equal to 1 instead of it gives you beta equal to half and gamma equal to 1 instead of beta close to 0.33 and gamma very nearly 1.25. So these are the right results, and this is what it gives. So it captures something, but does not capture everything. What it leaves out is the fluctuation. Instead of using fluctuations, it is using mean values of the pressure and temperature, and therefore equitheories of this type, as typified by van der Waals equation, are known as mean field theories. So mean field theories, you see what they are doing over here is that it takes a region of space where the density there are density fluctuations, ignores the fluctuations and focuses on the mean values. So that is what is going on in this, and therefore it pays to look at the mean field theories more closely, so that you also know how to improve on the mean field theories. So far as van der Waals equation goes, if this is your starting point, that's it. I mean, you can't improve. You know that you have got the answer wrong. You have got half instead of 0.3. You have got 1 instead of 5/4. But it's van der Waals that you are stuck with. So therefore, you want to look at theories with somewhat more microscopic leaning. So what we want to do is talk about the magnetic transition. So here is the van der Waals, it's a liquid gas transition near the critical point, which is a special feature of the PV plane. I mean, here in this large PV plane, you are picking out a small region where you want to concentrate. On the other hand, if I'm talking about, it is somewhat easier to talk about a magnet which at high temperatures is a paramagnet, which means the average magnetization is, there is no spontaneous magnetization. There is magnetization only if you switch on a magnetic field. So zero field magnetization is 0. So this M is essentially what is called the zero field magnetization. And that is 0. So this is temperature over here. High temperature, the zero field magnetization is 0. And then there is a critical point, Tc, and then the magnetization starts growing, and you have a magnetization versus temperature curve, which goes like this. And it is the susceptibility near this point over here. The susceptibility is proportional as T minus Tc to the power gamma, and the coexistence curve has M, the magnetization proportional to Tc minus T to the power beta, and at T equal to Tc, the M is proportional to, if I have an external field, then it is like H to the power 1 over delta. So that is the magnetic language. The susceptibility goes like that. And this is somewhat easier to, I mean, over here, I start with van der Waals equation, which means that I'm starting out with an average description. And it is very difficult as such to start with a description which is valid on the local scale. With the magnet, life is simpler. You can start with a local description, and the easiest is to start with a lattice. So you imagine a lattice, let's say a square lattice. I'll talk in terms of a square lattice because it's easy to draw. What holds for the square lattice holds equally well for the cubic lattice. So instead, it could have been cubic lattice, or it could have been a straight line. So this is 3D, this is 1D, and this is 2D, which for drawing purposes, I will use the 2D. So I imagine that at every point, every vertex has a magnetic spin. Ith vertex spin is SI, and it can only SI is equal to plus minus 1. So only up or down. This is the easiest model that you can have. In reality, the spin is a magnetic moment. It's a vector, and it sits at this vertex and can go around and do whatever it wants in a complicated motion in 3D. But we are going to assume that it can only point up and down, makes like so. This simplification of up and down is called Ising model, assigned as a PhD problem to Ising by Lenz in the late 1800s. And what is the specification of the Ising model? The specification is that I want to see the magnetization set in this problem, and I have a local interaction among the spins. The local is nearest neighbor interaction. So it is SI, SJ. I is the site. So in general, I mean, so imagine so that I don't have to write too much. These I's and J's are actually vector quantities. It's certainly for a 1D chain, it is 1, 2, 3. For like this, I has 2 coordinates over here. For the cubic thing, I has 3 coordinates. So it is SISJ, that is the interaction, and it's an attractive interaction. So it is with a coupling constant J minus J, SISJ, J greater than 0, I and J are nearest neighbors. So what is the total energy of this system over here? The total energy is which comes from the interaction between the spins is minus J SISJ. This is the ferromagnetic Ising model for which J is greater than 0. The antiferromagnetic situation is far more complicated. You would have these alternating attractions and repulsions. So we'll stick to the ferromagnetic interactions for at least, I mean, for most of the time. It's a ferromagnetic Ising chain or Ising lattice and so for that, J is greater than 0, and the energy expression is given by this. If I have a external field, small external field applied to the system, then H is the direction of the field, and then it is HSI. So that is the energy coming from the external part, and that is minus HSI. So H is a external, small external field. That is necessary because I would be interested in probing things like susceptibility. And if you are looking at the question of susceptibility, you would like to have an external field, and it is for a small, the susceptibility is defined as change the external field slightly, how much does the magnetization change? So del M del H at constant temperature, isothermal susceptibility. And so you switch on take h equal to 0, switch on a small bit h, and you look at m over h. So that's the Ising model. And the
Sir?
question is, yes?
So there is someone in the waiting room. Could you let her in?
Oh. Oh. So the question is that how do I calculate the magnetization, which is the expectation value of SI, and the susceptibility and things like that for this model over here. So, all right, obviously it is not going to be easy. So the first thing you want to do is make this So the first thing you want to do is, had it been a linear model, then obviously had this, here is the interaction part. What makes the model difficult is this term SISJ. It is the coupling which it is the interaction between the spins, which I have modeled by very crudely, but modeled the interaction all right by this term over here. And it is that interaction which makes the calculation very difficult for me. And therefore, what would be easy for me? That easy would be if this were a linear term in S, and then of course you know how to calculate, do the partition function trivially, and you get the answer. So all right, therefore what the first desire is, can I make this term a linear term? So linear term means that you play the game that you write SI as being SI minus average value of SI plus, S plus average value of SI. Average value of SI is your magnetization M, and therefore this is equal to SI minus M plus M. So this is the magnetization, just the overall magnetization per spin of the system if it exists, and this is the fluctuation around the M value. So here is this total spin has an average part which may be 0, and then there is the fluctuation around the average part. And so what do I do next? What I do is I write this SISJ as being SI minus M plus M into Sj minus M plus M, and write this whole thing as Si minus M into Sj minus M minus plus M times Sj plus M times Si plus M squared. So up to now, I have done nothing. And now I do something, and that something is, I claim that fluctuations are small and can be dropped. So I'm making the van der Waals statement, essentially. The van der Waals gas dealt with mean values. It was the mean pressure and the mean temperature, and they got related by that equation of state. I'm making the same. I started out ambitiously. I have defined this model, but now I'm in, when it comes down to a first stab at that model, what I'm doing is exactly the van der Waals assumption, except that now you can see it clearly. By writing SISJ, which is a genuine interaction term, in this form over here, and dropping this term over here, I reduce the energy expression to e to the power minus jm summation sj minus jm summation si, and then it is, so it's your s, you are multiplying out, and here is an sj si, that's your sj si over here. M square is a constant, so it's not going to play any role for me, and then it is minus hsi. But these two terms are the same, so it is minus 2mj summation over si. This gives the same answer as this, minus h summation si equal to 2mj plus h with a minus sign and summation s. So by one stroke, you have reduced a very complicated problem to a trivial problem. Because now the partition function, it's a non-interacting system. It has become a non-interacting system, and therefore the n-particle partition function is zs times to the power n, the single particle partition function raised to the power n, and then it is equal to sum over s equal to plus minus 1, and you have e to the power 2mj plus h times s. So s, which is an si, I mean this is z single particle. So z single particle is equal to yes.
Sir, I have a doubt, sir. In first two terms, the summation is over summation over I comma j. So but you have replaced it to summation over just I. So can you please explain it, sir? Again, that part.
I mean, this term is the same, I mean, exactly equal to this term over here. I mean, I'm summing over I and j, which are independently summing over I and j, keeping the nearest neighbor. And therefore, so consequently, now what I have is that I have a, let's say, this business over here, and I'm going to look at, essentially it's a question of we have broken it up into couplings which are essentially, I have JMSI. There is one term which essentially looks like this, another term which looks sums over there. So you are looking at a couple of terms which is JM, SJ and JMSI summed over the nearest neighbors over here. What you are worried about, that should I have reduced it because it was a sum over nearest neighbor, that what you are saying is that it is a J. So if I took S1, S2 plus, let's say I have S1, S2, S3, S4, then it is S1, S2, S3, S3, S4 plus S4, S1, and for each of them, so it is this interaction over here is changed to J. One of them, S1, S3, S2 has become the same as J4. I mean, if this were essentially vertical coupling, and then you would have that all these would come with a J1 and all these would come with a J2. So it would have been J1 plus J2, and since they are all the same, you pick up, instead of J1 plus J2, you pick up 2J. So that seems that's just the counting why the 2. That if this was a model which had a J1 coupling in this direction and a J2 coupling in this direction, then you would be picking up J1. So you would be picking up a J1 and nearest neighbors here, and a J2 and the nearest neighbors here. So you would be picking up a J1 plus J2.
Got it, sir.
So it's a question of not particularly important, but that's the way I would yeah. Meaning, SI minus SI average is just the local fluctuation. It's the local SI is broken up as SI minus mean value of SI plus SI, the mean value of SI. Are you asking about how the mean value of SI is calculated? Mean value of SI has to be over all sites and the same for all sites. Yeah. So average SI is finally this M over here. That's why I have replaced the average SI is an average over the lattice, and it is the number M. Yeah. So it is the total magnetization per site. It is averaged over all the sites and divided by the number of sites. So M is the average per site. So that is, the spin at the particular lattice point SI, and you are taking averages over the entire lattice dividing out by. So M is that divided, total divided by. So it's a this is the fluctuation at the site I, this is the fluctuation at the site J, and the fluctuation squared term has been dropped. So the energy expression has become this trivial quantity, which immediately tells you that the answer is this plus that. And so it is 2 cos hyperbolic 2mj plus h. So if s is equal to plus minus 1, that is your answer. The Zn is this raised to the power n. So it is cos hyperbolic 2mj plus h raised to the power n. So free energy, that's free energy is minus kT log z, which is equal to minus nkt log of 2 cos hyperbolic 2m, should have been a beta over here, right? Missed this. Continuously missed. Beta beta. Yeah.
Sir, in the partition function expression, S is equal to summation over all SIs, no? That this is the partition equation, partition number.
What are you saying? What did you say? The audio is not very clear. Just go slowly. What are you saying?
So that S, that big S in the partition function, that is equal to summation over SIs, no?
Yeah.
Okay, and then yeah, then that summation becomes a pi function outside multiplication function. Where-
Look, I couldn't catch the last part of what you were saying, but the energy expression has become particular in pair that has reduced to this expression over
Yes, sir.
here,
Yes, sir.
and therefore it is e to the power minus all these terms which are independent, essentially 2mj plus h si, that is one term, plus there is, so e, that is e to the power, and the
multiplication.
minus another. So this is, let's say, this at site s, the site meaning a site vector, and then there is the 2mj plus h, another site which is and so at every point there is a spin s which can point up and down, and for each one of them the contribution is 2mj plus h into that s over here.
Okay,
So
okay. That's single particle partition function. अच्छा अच्छा हाँ ठीक है सर. Yes sir. ওটা single particle partition function ছিল. Therefore I was confused. ঠিক আছে sir.
Here. So here is this. Total number. So this n, which is the for all these, essentially n sites all over them. At each site you carry out this sum, and if there are total n, then it is each one multiplied independent, and that's that. Except that I want a beta over here. Yeah. So it is, that's oh no. Sorry. But 2mj plus h times beta. So that's the free energy. So now what is this free energy? It is in the presence of a magnetic field. So it is E minus mh minus ts. So E for just a free particle, without a magnetic field, that's the energy. With the magnetic field, that's the energy. The magnetization times h has to be brought in. So sorry, this is the F, the free energy, total energy of the system. This is the part without the magnetization, and that is the contribution from the magnetization, minus ts. df is equal to dE minus mdh minus hdm minus tds minus sdt, and the tds removes the dE and the hdm. So this and this goes. So this is minus mdh minus sdt. So del f del h at constant t is equal to. So the prescription.
Hello, sir.
What happened?
Hello, sir.
Yes.
Sir, what is E here? Sir, can you repeat what is E here? Which energy?
The actual energy of the system, the energy that it gets from Brownian, from the random motion and from its interaction with whatever external agents there are.
Okay, sir.
So del F, the free energy is E minus Ts. Generally, when you write down E minus Ts, that is in the absence of any magnetic field or anything. The E is just the internal energy coming from the thermal, from the your random motion of the particles. If now, in addition, I have a potential energy that which has to get in over here, the potential energy is minus mH, so that's entered the picture. So the free energy is total energy of the system, energy as mechanical energy as defined normally, minus T times S, and this is the thermodynamic free energy, which is mechanical energy minus Ts. So del F del H is minus M, and therefore I need to take a derivative over here to get at this is free energy, and this has to be M, which is total magnetization. Should have need to be a bit careful about the notation here. I'm being sloppy. M is the spur average site. This M should have been, I mean, really the capital M, the magnetization of the system, extensive, intensive, and one needs to be careful. Sorry, I should have written the extensive quantity as capital M. So capital M is simply capital N times the individual magnetic moment, which is this, and therefore small m is equal to, so here is del F del H, which is to be taken, the KT which sits outside over here, and then it is a log, and so the one this comes in the denominator, so there is a 2, and the cos hyperbolic of this, and then you go to the top, you get a sine hyperbolic of this, and so the sine hyperbolic, again the cos hyperbolic, gives you a tan hyperbolic, which is 2mj plus h times beta, and then it's a derivative with respect to h, so I get beta down. So this there is a beta overall. This beta is inside the argument over here. So 2mg jv plus h times beta, and then a half which goes or stays. There is a half downstairs. I'm doing calculation with so it is with the derivative, so that means I am I have a 2 over here, is that right? It's a log 2, no sorry, there can't be a 2, it is sorry it's a log 2, so, and then it is a log cos, and so that's not there. So m is equal to beta kt, and beta kt is equal to 1, so out goes this, and I have m equal to, so the magnetization is to be obtained from this condition over here. So all right, so we need to so m is equal to tan hyperbolic that over kt. Let me do redefining, let me call 2mj divided by kt as being equal to x. So 2mj divided by kt as x, yeah, right? I mean, that makes good sense. Yeah, sure. So, all right. That means this m over here is going to become kt over 2j times x, and this is equal to tan hyperbolic, and that is your x over here plus h divided by kt. So kt over 2j times x is tan hyperbolic x plus h over kt. So I want to look at h equal to 0. Is there any magnetization? Because I want to ask a question, is there any spontaneous magnetizate? Spontaneous, meaning that there is no external field, yet the system wants to line up and provide some magnetization. It is just done by cooling the system, and the question is, does that happen? So does that happen? Is there any, so h is equal to 0, and it is kt over 2j times x is equal to tan hyperbolic x. So I have to solve this equation over here. So I plot it against x. So here is the plot against x. Tan hyperbolic x is a curve which starts out linearly over here, then bends and goes like this. So that's tan hyperbolic, a linear start and goes. The slope, the linear slope is unity. So it should have been like more 45 degrees. Yeah. Something more like this, right? That still is not quite 45, but better than the one which I had before. So it starts linearly and then sort of bends and there. All right. So now that's the right-hand side. What is the left-hand side? The left-hand side depends upon the temperature. So if the temperature is if kt over 2j is greater than 1, then the slope is greater than 1 over here, and the curve is going to look like this. So this side is going to look like that. This is if kt over 2j is greater than 1. And if it is lower than 1, then it is a lower slope over here, and you get a second in. So this is for kt over 2j less than. And now you see, when it is temperature greater than, if it is T greater than 2J over K, the only solution that your system has is M equal to 0. So at these high temperatures, there is no spontaneous magnetization in the system. But should the temperature become smaller, there is, I mean, for T less than 2J over KT, the KT over 2J less than 1, there now you have a solution where there are two possibilities. You have M equal to 0 as a possibility, and you also have a non-zero. There is the possibility of a spontaneous magnetization, which is this point over here to come in, appear in the system. So that is the critical temperature. So your critical temperature is KTC divided by 2mj is equal to 1. So KTC over 2mj equal to 1 is the critical temperature over here, and above that Tc there is no spontaneous magnetization. Below that Tc there is this spontaneous magnetization. So that's point number 1. That here is this is exactly the same thing as what you saw in van der Waals equation. So van der Waals equation showed you that there is no delta rho. The corresponding the magnetization analog for van der Waals is delta rho, which is rho liquid minus rho gas. So that is the quantity which is 0 when you are above Tc in van der Waals, and below Tc it becomes non-zero. It is the analog of the magnetization. The magnetization over here is 0. It's a spontaneous magnetization. The zero field magnetization is 0 above Tc and non-zero below Tc. So this delta rho, the delta rho of van der Waals and the spontaneous magnetization of the magnet are analogous quantities. So they, in any second order, this phase transition without any latent heat, just by changing the temperature, you are causing a spontaneous change in the property of the system. So without any question of latent heat coming into the picture, there is a quantity which is 0 above and non-zero below. So the characterization of this second order transition is by the existence of a quantity which is 0 above the transition and non-zero below the transition. All these transitions have the primary quantity is this kind of a variable which is known as the order parameter. So the density difference is the order parameter for the liquid gas transition. The magnetization is the order parameter for the magnetic transition. We have taken a very special kind of magnet. It can only point up or down. So it is like a scalar quantity, does not have a direction, can have only plus or plus 1, two values, plus 1 and minus 1. So it is a very special kind of magnet. More normal would have been to have a vector. So in which case I would have to use the spin as a vector, and it would be SI vector, and then the order parameter would become a vector quantity. Over here, the order parameter is a scalar. In the liquid gas transition, delta rho is a scalar. Over here, in this, what we will call the Ising magnet. So for the Ising magnet, the magnetization is a scalar quantity. When the magnetization becomes a vector quantity, where this is what will be called a Heisenberg magnet. And what we have said so far has nothing to say about, has nothing to do with what you are seeing on the board. What you are seeing till now is completely a question of a scalar order parameter. For the magnet, it is the Ising magnet which can point up or point down. So the order parameter, you see, can be a scalar or a vector and so on. And the vectorial nature of the order parameter is generally characterized by a number n. The dimension of order parameter vector is generally, so dimension of order parameter vector can be n, which is generally denoted by n, and it can be 1, 2, 3, and so on. And then there is the spatial dimension. The spatial dimension, which is d, and can be 1, 2, 3, and so on. So there are two distinct dimensions in this problem. There is the dimension of the order parameter, which can be 1, 2, 3, and can be the space. So it could be a Heisenberg magnet sitting on a one-dimensional lattice. So I can have a one-dimensional chain at every point. I mean, so you have a lattice, 1D lattice, like there's a point over here, point over here, point over here, point over here. And the spin that sits over here can be a Ising spin pointing up or pointing down, or it can be a two-dimensional spin so that it can only move in a plane. So let's say the plane over here, and the spin can only move in that plane over here. Or it can be d equal to 3, so the spin can rotate like this, and the spin can also rotate like this. So three-dimensional magnet on a one-dimensional line, two-dimensional magnet on a one-dimensional line. And similarly, it can be a one-dimensional magnet sitting on a two-dimensional lattice or a three-dimensional lattice, and so on. So these are two independent quantities. The n and d are independent of each other. D equal to 1 can have n 1, 2, 3. D equal to 2 again can have n independently 1, 2, 3, and so on and so forth. So the things like the critical exponents would be, you will find, be determined entirely by the two dimensions n and d. So all right, for now it is all mean field, and we have, what we have done is shown what is a mean field approximation, and within this mean field approximation, we have found that the transition temperature is. So now we need to find the critical exponents. So I need to find the critical exponents. And that, let's say, so I go back to my starting equation, which is this over here. I'll write it in the form m equal to tan hyperbolic. This x is easy to write for drawing this graph over here, so that I have only one tan hyperbolic to draw, and just can tilt the straight line. But once that is done, I would like to go back to m equal to, so this equation in its original form, that m is equal to, so what was the, here is x, so this cancels out, and this is m, and this is equal to tan hyperbolic, and it is h plus 2mj divided by k. So that's my And let me talk about T less than Tc. So T less than Tc, so T is equal to Tc into 1 minus epsilon. Epsilon is much, much smaller than 1, and therefore M is small. So M is 0 at epsilon equal to 0, and now your M is epsilon is slightly lower than 1, so which means you are slightly below the critical temperature, and your M is small. So I'm going to expand the right hand side. The H is and I'm going to look at first thing to look at zero field magnetization. So zero field magnetization, so external field H equal to 0. So M is equal to tan hyperbolic 2mj over kt, which is equal to, so it is tan hyperbolic T is Tc times 1 minus epsilon. So it is 2mj divided by ktc into 1 minus epsilon to the power 1. But this 2mj over ktc is equal to 1, and therefore this is equal to tan hyperbolic 1 minus epsilon to the minus 1, which is tan hyperbolic 1 plus epsilon square plus epsilon cubed, and so on. So that is equal to yes. What did I do for this TC? Sorry, no. Where did I? Yes, right. It's TC, and it is M is equal to 2mj, and that is no. It is Mr. M. Mr. M. Mr. M. So here we are. Yeah, thanks. So that's equal to tan hyperbolic time. So term number 1, tan hyperbolic expansion, M into 1 plus epsilon square, so on, minus 1/3 into M cubed into 1 plus epsilon square, so on to the power 3. So this is equal to M over here. So this M cancels. So now you have M epsilon, the first term, and so 0 equals M epsilon. That's the first non-vanishing term from over here. And now when I do this one over here, it is going to be just 1. So it is minus M cubed divided by 3. So M square is equal to 3 epsilon, M equal to root plus minus root 3 epsilon to the power. So there you are, the exponent. So we get the exponent beta very easily. The exponent beta for this transition is beta equal to half. So beta equal to half, exactly the same as the van der Waals answer. So when we did van der Waals, we found that beta is equal to half. And once again, over here, I do this calculation near the critical point, and just below the critical point, and you have M equal to root 3 times epsilon to the power half. Now, this, I mean, this is somewhat startling in the sense that you are looking at two very different systems. But if you are just sitting in the vicinity of the critical point, then everything seems to be swamped out, and it is only the question of the order setting in, and the order seems to set in somewhat independent of everything. All right, so now it's a question of calculating the susceptibility. So susceptibility, and I have to do del m del h, that is take a derivative with respect to it. Now susceptibility chi is equal to del m del h. This is the isothermal susceptibility, which means that I'm looking at a fixed temperature and taking the derivative of h of m with respect to h. So it is del m del h, and this is equal to, so it's a derivative of this with respect to h. So it is tan hyperbolic square is going to be sec hyperbolic square h plus 2mj divided by kt. So tan hyperbolic square, tan hyperbolic, it's a derivative with respect to this, and then the derivative with respect to this, the derivative is a sec square hyperbolic of this, and then with respect to this, it is 1 plus 2 susceptibility del m del h j divided by kt. So you take a derivative with respect to h, and you pick up chi is equal to sec. So I'm now above the, I'm going to set myself above the transition, and it is the zero field susceptibility. So I'm going to actually should have actually said this before, that it is pi, it's a zero field susceptibility del m del h, h tending to 0, and I shouldn't have, I should have could have got this was unnecessary trouble here. Sorry, we'll need that later, but not now. So zero field susceptibility, so it is 2mj and 2 pi j over kt over here, and that is your 2m. So the sec hyperbolic square, the sec hyperbolic square is cosec hyperbolic square, which is one of these inverses over here. It's a tan hyperbolic giving you a sec hyperbolic. It's a 1 plus 1 over. So this is 2 chi j over kt, which is divided by cos hyperbolic square over here, which is 1 plus, so this is a 1 over cos hyperbolic square, and the 1 plus cos hyperbolic square is 1 plus sine hyperbolic square 2 over mj by kt, So this is chi equal to, so this is equal to something where is my 1 plus cos hyperbolic sine hyperbolic square, which is going to become small over here. Here is j over ktc. So this is equal to T is equal to Tc times 1 minus epsilon. So this is 2 chi j divided by Ktc, T, and then it is 1 minus epsilon over here. So chi of t over here is t is equal to t minus tc into 1 plus epsilon. So it is tc into 1 minus epsilon. 2j over ktc is equal to 1. So this is equal to chi into 1 minus epsilon and divided by, so it is chi and 1 minus epsilon. Where is my constant term? Sorry. Too bad. It should have been, I'm looking at m equal to tan hyperbolic h plus 2mj divided by kt, and it has to be a zero field. So take derivative first and then set h equal to 0. So that was an error. Should have taken a derivative first and then set h equal to 0. So first derivative sec hyperbolic square 1 and sec hyperbolic square h plus 2mj. So this should have been h plus 2mj sec hyperbolic square. Then the derivative of this with respect to h. So that should be a 1 plus, sorry, that should have been, should have kept that for this derivative here. So this is not important, but that is. So it is a sec hyperbolic square h plus 2mj over kt into 1 plus 2 chi j over kt. Take h going to 0. This is not important over here, and I should have had 1 plus 2 chi j over kt. That part is 1 plus 1 over cos over 1 plus sine hyperbolic square. So this is 1 plus this over here, and the sine hyperbolic square m going, this is small, so I don't want that. So this is, sorry, it is 1 plus this, and then this is square of, this is like m square, and therefore being dropped. So this is equal to 1 plus 2, this is chi into 1 minus epsilon, and therefore chi comes to that side, and it is epsilon chi equal to 1, and chi is equal to 2. So all right, so that's that. The susceptibility epsilon chi, sorry about that, should have dropped it after taking the full derivative. So droppable here, but not droppable when I'm doing h derivative. So 1 plus 2 chi j over kt. So this is sec hyperbolic square coming as 1 plus sine hyperbolic square. But small m, sine hyperbolic square is like m square over here. So small compared to 1 dropped over there. And it is the numerator, which is 1 plus 2 chi j and 1 minus epsilon. This part is big and cancelling out over there, and it is chi. So 1 has to balance out the chi times epsilon. And so that is the divergence of the isothermal susceptibility, chi proportional to T minus Tc to the power. So once again, absolutely similar to the van der Waals gas. Just as it was isothermal susceptibility proportional to 1 over T minus Tc over there. It is 1 over T minus Tc over there here. So the magnetization goes like T minus M proportional to T minus Tc to the power half magnitude, chi proportional to 1 over T minus Tc for T greater than Tc. The slightly more ambitious calculation is now to do the susceptibility for T less than Tc. There is an interesting issue over here, and therefore this actually needs to be done and done somewhat correctly. So this can be a bit of a bother, but the point, it is very rarely that one would be doing calculations below Tc, and this is one where after all it's mean field and one should be able to go through it. So, and get the right answer, because the right answer, the final answer is actually important. Up over here, for T greater than Tc, I have got chi equal to 1 over epsilon, where epsilon is equal to T minus Tc over Tc. So that's the definition of epsilon, T minus Tc divided by Tc. It's a number, and chi is equal to this calculation. It is all, I mean, it's the prefactors which I'm now worrying about. I want to make sure that the prefactors are right. The proportionality is no longer the question. Proportionality, fine, it tells me that gamma is equal to 1. So T greater than Tc, it is proportional to this, and therefore the exponent gamma is equal to 1. Beta is equal to half, gamma is equal to 1. And but the exact answer is chi is equal to 1 over epsilon. Epsilon is T minus Tc over Tc. Now I want to look at this below the transition. So M is equal to, so we found before this, we had obtained that M square is equal to 3 times Tc minus T. So if I'm below that was again the right exact answer, that M square was 3 times Tc minus T. There again, I think that there should have been a, must have been a Tc below. Yeah. Has to be. The epsilon defined correctly. So M square was 3 times 1 Tc over minus T over Tc, and that was the answer. And this is, I'll need that, because now I want to look at this quantity for T less than Tc. So T is going to be Tc into 1 minus epsilon. Over here, it was T equal to Tc into 1 plus epsilon. Now I'm going to set T equal to Tc, 1 minus epsilon. And then I know that M square is equal to 3 times epsilon. And therefore, I mean, this is 3 times this. So M square is equal to 3 epsilon over here. So M has to be a non-negligible quantity. So once again, the susceptibility has to be found, and it has to be the same statement as over here, that chi is going to be equal to, so that relation is del m del h, and it would be for h tending to 0, and this is equal to sec hyperbolic square. So this is equal to, that part is quite all right, which is h. So m is equal to tan hyperbolic this. Just trying to make sure how much can I take from, borrow from here. So it is sec hyperbolic square h plus 2mj by kt, and here is the derivative 1 plus 2 chi j over kt. So everything looks right. So this has come to this, right? So one, I have made no so let me get rid of that. It is now 1 plus 2 chi j divided by kt divided by, so it is 1 plus 2 chi j divided by kt, and that divided by 1 plus sine hyperbolic square 2mj divided by kt. So that part of it is holds without any doubt. So this is the part of it, and now the game changes because I am at t equal to tc minus epsilon, 1 minus epsilon. So up over here it is going to be, so it is going to be 1 plus 1 over, so 1 over ktc, that's this term over here, 1 plus epsilon, 1 minus epsilon to the power minus 1, 1 plus epsilon square, plus 2, so that's the first term over here, plus 2 chi j over ktc times, it is tc over t. So just looking at, let me write down the numerator. So numerator is this plus this is equal to 1 over ktc, 1 plus epsilon square, plus 2j over ktc is 1, and now it is ktc divided by t, and therefore it is tc into, so it is 1 minus epsilon to the power minus 1. So it is chi plus 1 over ktc, that into 1 plus epsilon square, and so on. So I've got the numerator hopefully correctly. So now I have to look at the denominator and get it right. So it is the denominator, and the denominator is 1 plus sine hyperbolic square 2mj over ktc. So I want to look at this denominator over here. So I want to look at the denominator, which is 1 plus sine hyperbolic, the m is a small quantity, so it is sine hyperbolic square, and then it is 2mj over ktc. This is t, which is 1 plus epsilon square, and so on. This is 1 over 1 plus, so it is sine hyperbolic square m square into 1 plus epsilon square and whole square, right? Sine hyper, so 2j over ktc is equal to 1, and then it is sine hyperbolic square m, or m is this, so it is n plus higher order terms, which is 1 minus m square into this whole square, so it is 1 plus epsilon square whole square, so 1 plus higher order terms. So this quantity seems to be equal to that. and therefore the chi which is equal to this. So now let's see, the chi was equal to this, that's the top. So chi is equal to, so this is chi. Chi is equal to this one, that's the numerator. The numerator is chi plus 1 over KTC into 1 plus epsilon square this. And then in the denominator, it is 1 plus 1 over this, which is 1 plus m square into that, which if I take into the numerator is 1 minus m square into 1 plus epsilon square and so on, which is equal to chi into 1 plus epsilon square. So on 1 over KTC into 1 plus epsilon square into this term is into m square is 3 epsilon. So this is 1 minus 3 epsilon, and maybe that's the 1 minus 3 epsilon. Where am I? It is 1 plus KTC, and then I'm looking at the denominator, substituting for m square, which is 3 epsilon, and then again it is going to be 1 plus epsilon square and so on. So this is chi equal, this is chi plus epsilon times chi plus 1 over KTC there is error somewhere. It is the 1 over this part is all right, so I get this, but there should have been a switch over here. How did I, what was the, something has gone wrong here.
স্যার ওই থার্ড টার্মটাই ইনটু কাই থাকবে স্যার। স্যার ওই 1 মাইনাস 3 এপসিলন ইনটু 1 প্লাস এপসিলন স্কয়ার স্যার ওই নিচে না না হ্যাঁ স্যার এইখানে স্যার ইনটু খাই থাকবে একটা স্যার কারণ আপনি যদি খালি অর্ডার এপসিলন টার্মস গুলো নেন স্যার, তো ওইখানে একটা কাই দিয়ে মাল্টিপ্লাই হতে হবে, মানে স্যার
এখানে একটা কাই, লেটস সি, একটা কাই 1 ওভার কাই ইনটু এটা এই হলো, তারপরে পরের টার্মটা হওয়া উচিত ছিল m স্কয়ার, m স্কয়ার কাই।
স্যার ওখানে একটা কাই থাকবে।
there is there is 1 plus epsilon square, kintu more yete jeta is there is a chi into m square. So that is sorry, yes, right, thank you. So plus 1 over 1 plus chi into 1 plus 1 over epsilon square. So there is this term over here, and then it is minus chi into, so it is minus chi into 1 plus epsilon square, this one into m square It is chi into this into minus m square, which is the bigger term, and that has to be the larger term over here. M square is proportional to this, so it is minus chi into the 1 plus epsilon plus epsilon square, which means that the chi is equal to, so this is the epsilon chi over here, and over here it is 3 epsilon, which gives me the 3 epsilon chi over here, and there should be a order unity term, which is the term over here, which is 1 plus KTC. So the order unity term over here is chi in 1 over kt. It is chi plus 1 over ktc. So there is chi, and then there is 1 over ktc, that is the 1 plus ktc. And then over here there is what I have already written, chi into 1 plus 1 epsilon square. Then I have to write chi minus m square into 1 plus epsilon. And this m square is like 3 epsilon. So this is chi, the one part, and then when it is epsilon chi, there is a contribution from minus m square into chi, which is 3 epsilon chi, and then there is the order unity term, which is this. So it is chi equal to that, which cancels out, and therefore chi is equal to 1 over 2 epsilon KTC. So that is the issue over here, that it is 1 over 2 epsilon. It was 1 over epsilon when it was above. The susceptibility diverges like T minus Tc to the power 1, both above and below. So it is T minus Tc to the power minus 1, whether it is above or below, but it is the amplitude which is the important issue over here, that the amplitude above and below are not the same. So that is the thing to focus on, that the amplitude above and below is a number half, which is again a universal number. So very close to Tc, chi greater divided by chi less is equal to 2, which is universal, which is independent of what kind of magnet that I'm looking at, and it is independent of the nature of the magnet and is a universal number over here. This is what you don't have in the van der Waals gas. So this is why the Ising has one interesting feature over and above the van der Waals gas, that if I look at the susceptibility, very close to Tc, susceptibility above divided by the susceptibility below is a universal number. So amplitude ratios, it is not just the exponents which are universal. You can also find amplitude ratios which are universal, and that is for this magnet, it is all right. So that this is where I will stop. We have done enough for a day. Just with one minor issue, which we talked about this model, my SI/SJ. So I had a spin up, spin down, spin models with SI being 1 or minus 1. I could equally well talk about this as number of atoms absorbed on a surface adsorption. So atoms come and get adsorbed on the surface. Some sites are occupied, some sites are not occupied. So occupied or not occupied. So Ni can be equal to 0 or 1. So that's again, I mean, the question of if you want to find out when there is a critical temperature, whether there is a critical temperature in this adsorption or not. It is similarly, it's a Ising situation, which you can think of the vacancies and the filled states interacting with each other just as these were, and now you can consider Ni to be defined as 1 plus Si divided by 2. If you start out from here and use a substitution, the Si is getting then the corresponding model that you are going to look like, write down, is going to describe critical behavior in the question of adsorption on a lattice. Similarly, if it were some kind of an alloy, which alloy AB with type A atoms sitting over here, type B atoms across sitting somewhere here, and the atoms dispersed at a given temperature in some fashion or other on the surface over here or on the vertices of a cube, what have you. Once again, it is the number NA and NB. You can think of them as 0 and 1, and you can do a similar kind of transformation and talk about this class of problems. So you have with this Ising a whole class of problems that one can talk about. It can be adsorption problems on a surface or on the vertices of a cube. It can be a binary alloy problem, or it can be a magnetic moment problem. All of them will have the same kind of critical behavior and so on and so forth. So this is the mean field critical behavior, and the mean field was essentially the question when we started out with this Ising magnet, very clearly showing what the mean field is. You threw out the product of S minus average S with itself. So you threw out, those were the fluctuations which you threw out, and those are the fluctuations which are responsible for changing the critical exponents. Your critical exponents, which came out as beta equal to half and gamma equal to 1, are not quite right. And the reason is that you threw out those fluctuations. So the point has to be that I have to start out with SISJ and try and do a better job. So that is going to be thing to. But the next class, what I'll do is, see, we have been talking about, today was entirely on a lattice. We started out talking about a gas, which liquid gas. Then today we switched to a lattice and got similar answers. On Friday, after which one has a break, I want to bring in the other class of problems that one needs to worry about, where it is not a question of these discrete spins Si sitting on a lattice, but a system, magnetization system described by a magnetization which is a function of the position coordinate. So we will talk about we will go from the lattice description we'll talk about a continuum. We'll start out with a continuum description, and it will, so how does one, what is a mean field theory? Over here, we did van der Waals starting out with a mean field equation of state, did mean calculation, found exponents, which were consistent with the mean equation of state that we started out with. Today, we looked at magnet much more closely by looking at the individual magnets which give rise to the collective behavior. And then you see that if you ignore the fluctuations, you get down to van der Waals. But it was a system on a lattice. What if it is a continuous system? Instead of talking about SI, if I talk about S, which is a function of the position variable, S as a function of the R vector. So the next class, we will do S as a function of S R vector. How does one go about setting up the problem? What is mean field in that context? And that would, at least, I mean, when you have the break, you can think about all the different mean field approaches. And when we, after the pujas, we can start talking about the discrete model, and when can you solve it exactly, when can you do some approximations. So that's the layout of what the next class, and thereafter where we will be headed. And so let's see. All right, so we'll see, meet on Friday.